We're cruising. Derivatives, as I mentioned previously, are very rote, procedural calculus computation, but we're definitely going to have to buckle our seatbelts because this might get a little bumpy. So, when dealing with trig, more often than not, we're kind of just told what the derivatives of our standard trig functions are. If you want to verify that that's the case, remember you can always default back to the definition of the derivative. But the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. We will, though, verify this just for fun. So, if we take our definition of the derivative, which says the limit as h approaches 0 of f of x plus h, so this is sine of x plus h minus sine of x divided by h. This requires an addition formula, not one that you would have to memorize, but if you look in the front of your textbook, you would find it. But this will expand to sine of x cosine of h plus cosine of x sine of h minus sine of x all over h. We have a common factor here, so give a little bit more space. So we can now say the limit as h approaches 0 of sine of x cosine of h minus 1 plus cosine of x sine of h all over h. We can, since we have a single term in the denominator, separate these two functions. Or these two terms in the numerator, apologies, not two functions. So sine of x cosine of h minus 1 plus cosine of x sine of h all over h all over h. Now, if we yank this out, because notice it's acting as nothing more than a numerical value since the variable that we have here is h. Right? So it's almost like scalar multiplication. Back in our exploration on limits, the limit is h equals 0 of cosine of a variable minus 1 over h tends to 0. So this entire piece here becomes 0, and we're left with this expression, which we can do the same thing. So the limit as h approaches 0, we can pull out cosine of x, since it's acting as nothing more than a scalar multiple, sine of h over h, which if you refer back to that expression, would be equivalent to 1, thus leaving cosine of x, which would validate the derivative of sine x. And if you ever come across somebody that tells you that you need to know all those addition and difference formulas, they're a bold-faced liar. But don't take my word for it. Now let's write down the derivatives of the, I like to call them the other guys. Gals. Right, because we always focus on sine and cosine, but d dx, so the derivative with respect to x of tangent x equals secant squared x. Oops, getting ahead of myself. Negative cosecant squared x. I hate to say this, but the only real way to remember these is via memorization, sooner rather than later, because you won't be learning remotely for eternity, and you will have to recall these. And if you're an engineer or a math major, you're going to have to recall them for at least the next 2 years in Calc 1 through Calc 4. Some of the tricks that I like is when I'm doing secant and cosecant, starts with S, right? So no cos here. Negatives, okay? Cos have the negatives. The non-cos are positive. And notice how I wrote them. I know that tangent and secant have to go together, so that must be secant squared, and vice versa. But I know you're not just sitting on the other end of this virtually, asking me to just write out the derivatives of our trig functions. So let's do a practice problem, but let's involve everything we've been talking about in our videos to date. So let's find the equation of a tangent line to y equals tangent theta secant theta at pi over 4. That should probably say at theta equals pi over 4. So notice, right, equation of tangent line, comprehensive idea behind a derivative. Tangent theta, secant theta, so we have the product rule, and we have trigonometry, so we got our work cut out for us. Y prime equals the first function times the derivative of the second. So look above your paper, the derivative of secant theta is secant theta tangent theta, plus the second function times the derivative of the first, so derivative of tangent is secant squared times secant theta. If you want to simplify, you're more than welcome to, but don't feel compelled to. Secant theta tangent squared theta plus secant cubed theta. So remember, what does the first derivative give us? It gives us the slope of the tangent line at this particular data value. So y prime of pi over 4 is going to be secant pi over 4 times tangent squared of pi over 4 plus secant cubed of pi over 4. At this point, you should be able to figure out what those values are for tangent and secant. Pi over 4 is the 45-degree measure, so we know that this is going to be a 1 no matter what. Secant is really 1 over cosine, and that means that at that value, that's 1 over root 2 over 2, so if we flip it, this becomes 2 over root 2, and if we do the rationalized denominator, this becomes, oops, erase that, multiply, right, those will cancel, so we're going to be left with a 2, 2 divided by 2 is 1, so this is really the square root of 2 times 1, plus, if secant of pi over 4 is root 2, so this is root 2 to the third power, which is really going to yield root 2 times root 2 times root 2, so that's 2 root 2, which is equal to 3 root 2. It's understandable if that's something that you're still struggling with, but you really have to get that unit circle mastered if you want to be successful as you get deeper and deeper into mathematics. So we have the slope of the tangent line. We are just missing our point, right? We have our input, our x coordinate, pi over 4. So y of pi over 4 is tangent theta times secant theta, which as we did before, tangent of pi over 4 is 1, secant of pi over 4 is root 2. So that is our output. So y minus root 2 equals the slope, 3 root 2, theta minus pi over 4. And that is your comprehensive package, bow on top. No pun intended. Stay tuned, we got plenty more action coming at you.